Thank you very much for this lovely presentation. Without further ado, let's move on to the next session. And let us remember Edmond Becquerel's contributions in the areas of phosphorescence. Handing over now to the two chairs of the session, Jean-Louis Lazari and Lawrence Peter. Hello, everyone. Can you all hear me? Yes, we can. My name is Jean-Louis Nazari. I'm a researcher at the CNRS Center in France. Right now, I'm in my living room. I'm a trained solid-state physicist. I specialize in semi-conducting thin films. I use a technique such as heteroepitaxy and also the physical properties of thin film for electronic applications. I started working on laser diodes and also infrared photodetectors, and more recently, I've taken an interest in intermediary band solar cells. 3-5 semiconductors in particular. I have the pleasure of chairing this session on phosphorescence and photoluminescence. Thank you very much. Jean-Louis, good morning, everyone. My name is Henry Peter. I'm a professor emeritus in Bath in the UK. For nearly 50 years, I've been working on photoelectrical chemistry, and I have the great pleasure of introducing Guilhem Gallot, the next speaker. He is the head of research at CNRS and also the Polytechnique school in Palaiseau, where he is also a teacher. Guilhem is well known for his work on spectroscopy, femtosecond spectroscopy in particular. Last year, Guilhem supervised a group of 5 Polytechnique students on the plan was to restore a Becquerel photophoroscope. There's an example of phosphoroscope that belongs to the Polytechnic School. I'd like to attract your attention to this quick video, which I put together on the building of a phosphorescope. We made it at the Institute, and I've worked at this institute for many years. Thank you very much. I'd like to talk to you about Edmond Becquerel's phosphorescope. More specifically, this is a collective project that we organized with Polytechnic school students, actually, last year. I work as part of the optics and bioscience laboratory, and I was involved in this project where I supervised the students. Now, the phosphorescope, the whole issue has to do with phosphorescence. What is phosphorescence? Well, phosphorescence is part of a bigger family, the luminescence family. And I'm referring to spontaneous emission of light using different energy means, quote unquote, as opposed to incandescence. Incandescence is the production of light by heating the material. So we're talking about cold light because the material is not being heated. There are many different examples. It all depends on how you activate production of light. Here's a very well-known example. LEDs, light-emitting diodes. So the light is produced by an electric field. However, I apologize for this technical glitch, says the speaker. I'm not seeing the slide that is being displayed. Well, I'm seeing it. Interesting. Something weird with my PowerPoint presentation. Anyway, so light-emitting diodes. Glowworms is an example of bioluminescence. And then what are we interested in today? Anything pertaining to photoluminescence, which includes fluorescence and phosphorescence. So, photoluminescence is the production of light by absorption of another light. So, what's the difference between fluorescence and phosphorescence? Well, we used to call it phosphorescence from phosphorus. We have a quote from 1789, and that's the property of giving off light without combustion. So that's an old definition for phosphorescence. The name fluorescence was given later by Stokes in 1852. So the main difference between the two has to do with the lifetime, the, the duration of the storage of energy, because time elapses between storage of energy and re-emission of energy. So you have time divided by tau, and energy decreases over time based on this characteristic time. So the difference between fluorescence and phosphorescence is mostly this. So for fluorescence, it's a short time, lower than 1 millisecond, sometimes as low as 1 nanosecond. But for phosphorescence, we're talking longer durations, over 1 millisecond, sometimes 1 minute, sometimes hours. And the difference is physical as well as human related. In actual fact, it is impossible to observe these characteristic times for fluorescence to the naked eye without an actual instrument. So if we want to go further, obviously, we need to move into the world of quantum mechanics. And that's something that Edmond Becquerel knew nothing about, but we have modern scientific explanations. If we go back to this specific metaphor of the foosball, and Daniel Lanco loves his foosball, the electrons, which have discrete states here, represented through discrete states, can change energy levels by absorbing photons. Through absorption, the electron is excited into a higher state of energy. Then this introduced the S spin state. So S equals 0, it's a singulate. And this is going well because the fundamental state has a level of 0. And according to quantum mechanics, the potential transitions are done while maintaining this number. So once the electron is excited into a higher energy state, it will release its energy, possibly by emitting a photon, and that's called fluorescence. And because the transition is mechanically possible, the release of energy, that is the emission of the photon, is done quickly, and we're talking about fluorescence. However, there are molecules in which the electron can switch to an S equals 1 state, so a triplet state, and so the electron should stay stuck forever. There are other mechanisms, as it happens, that allow for the transfer of energy toward the fundamental state. And when you have states that are stored for much longer, we talk of phosphorescence as opposed to fluorescence. Let's quickly look at the history behind the Becquerel's phosphoroscope. When Becquerel made that discovery and started working on phosphorescence, obviously he built on the past 30 years. And here are a couple of important examples of the work done over the past 30 years. Now, we discussed some of them earlier this morning. In 1821, Fraunhofer started looking at the emission spectrum of certain materials, and he found what was later termed Fraunhofer's lines. And so this work was also driven by the discovery of photography in 1827 and the following years. As a result, emission spectra were collected by museums as a basis for their work. In 1852, Stokes observed that the absorption spectrum, in other words, the different colors absorbed by the materials, was different than the colors re-emitted by the very same materials. And this effect was quantified by Stokes. So there was a delay, a shift between the emission maximum levels, and Stokes called it fluorescence. There's an analogy with opalescence, as in opals, but he used the term fluoride, and fluoride gave its names to the term fluorescence. So this brings us to 1857 with the creation by Becquerel of the phosphoroscope. And this is a photo of the phosphoroscope at our school. And this is the first mechanical instrument making it possible to study the lifetime of these phosphorescent states with a resolution that is much less than 1 millisecond. There are different types of phosphoroscopes, and you find them in different collections in Harvard, in Aberdeen, at CNAM. This is the Harvard one. It's a portable phosphorescope. And I think it must have been pretty tricky to handle. But this is a more miniature version of the larger phosphorescope that you can see in the lower left-hand corner. Now, what's the underlying principle behind the phosphorescope's operation? Obviously, no invention is based on nothing. You don't pull it out of your hat. There are two prior examples of similar machines that were probably helpful to Becquerel when he designed his own phosphorescope. So 1834, Charles Wheatstone developed a rotating mirror to measure the velocity of electricity transmission. And this mirror was taken up by Hippolyte Fizeau 15 years later. So he modified the mirror. So he used a rotating wheel. And this is a close view of the multiple teeth, the serrated edge of this wheel. And when you rotate the wheel very quickly, you measure the velocity of light. That's what Hippolyte Fizeau did in 1849. So Becquerel took up the same idea. So he used quick moving mechanics to measure phosphorescence related phenomena. So he used two rotating disks. And this is what you can see on the engraving. I can give you more details on that in a couple of minutes. So two rotating disks at a high speed. So he used a crank and a series of cogs and wheels. And so there are openings in these two wheels, but the apertures from the two wheels are not in line with each other. So a quick story. Becquerel's own son, Henry, was interested in phosphorescence, and he discovered radioactivity fortuitously a couple of years later. At the end of the 19th century. So as you can see, there's real continuity in the Becquerel family from father to son to grandson. Now, a more modern interpretation, a more modern explanation won't be available until the early 20th century with the development of quantum mechanics. And more specifically, in 1921, the Kerr effect, the electro-optic effect. This led to the manufacturing of new machines based on different mechanisms. And obviously, the resolution drops to 100 nanoseconds, and that's thanks to electric impulses. Now, what's the underlying principle of the Becquerel phosphorescope? Here it is. You have two rotating wheels, which are synchronous relative to each other. And there's a crank, and you turn them manually. So the light comes here from the left. Either it is blocked by the first disc, or it goes through, but then it is blocked by the second wheel. So the light can never escape both discs. It never makes it past the second disc, the second wheel. So Becquerel used the sun as a light source. He also used oil lamps, Carcel type oil lamps, because he needed a strong lighting for his experiments. So this is what happens. Becquerel puts a phosphorescent sample between the two wheels. So the phosphorescent material is going to store the energy and release light after a certain time, usually 1 millisecond. And this is what happens. When the disk turns quickly enough, the energy drops after excitement and is strong enough to escape. So part of the light escapes. So the quicker you turn the wheels, the higher the amount of light that escapes is. And this is how Becquerel is able to measure the characteristic phosphorescence times by measuring the rotational speed of the wheels. More specifically, you see the charge and discharge cycle of phosphorus. When the first wheel is open, the phosphorus becomes charged. Then you block the light source, the phosphorus becomes discharged until the next cycle. And in between, the exit window opens, which means that you integrate a signal. And this signal is symbolized by this whole time or temporal area here. Now here Becquerel obviously had nothing but the naked eye, but now we have other equipment, cameras, etc., to quantify that time. Now, this is the historical instrument devised by Becquerel. See the crank? You use it, and there's cogs and wheels that you use in order to turn the wheels, and this is the observation element. And the area where you put in the phosphorus sample. And then you have a base made out of wood, and inside that drawer you still have samples, and we don't know whether Becquerel used those samples or not, or whether they were used at a later stage for demonstration purposes during classes at the Polytechnique school. I have a video here. Just watch. You should be able to hear the sound that the device makes. See the entry window? And the wheel is turning faster and faster. And then you have the second wheel, which is symmetrical, which is on the other side. Okay? So we're facing the wheel directly. And as you can see, at no time do you see through both wheels. The view is always hidden. And these are the cogs and wheels that you see at the bottom, and the crank, which you turn manually. Now, here we're turning the crank very slowly. So if I move away from the instruments, see, we're turning the crank rather slowly, but you can still hear the noise that the instrument is making. Now, in order to reproduce Becquerel's experiment, it's kind of difficult to use the instrument itself because it's a work of art, it's a historical artifact, but to reproduce these rotational speeds, if we look at the publications, we realize that Becquerel reached 3,000 to 4,000 hertz. That is, he turned it 3,000 or 4,000 times per second. So I imagined a more modern system, a simpler system to reproduce the experiment. We based ourselves on off-the-shelf systems. So a commercial motor, commercially available motor that we use for chopping the light for scientific experiment purposes. So we used an LED as a light source, a blue light source to excite the phosphorus. The phosphorus was donated by Thierry Lacroix, who's a researcher at the condensed matter laboratory at Polytechnique. So we're using europium chelate, which is particularly effective for these types of experiments, and finally 3D printing. We used a 3D printing for the hood and other mechanical structures. We carried out a number of experiments looking at what was happening either with the naked eye or using a camera or amplified photodiodes, which allowed for more accurate measurements. And this is a video of the device while in operation. See that this is the blue light source and the phosphorus, which is excited by the light, and the detection system that can quantify the measurements. Now, this is the experiment as Becquerel must have or could have carried out back in the day. So we placed a source of light at the back. You see the phosphorescence coming through. On the side, that's parasitic light. And you can you can hide it using caches, but I remove the caches for the sake of experiment. As you increase the rotational speed, as you can see, the phosphorescence emerges and actually gets through. So we are reaching the maximum speed here. It's already pretty noisy. 1 kilohertz, that's the modulation. And now we're reducing the speed again, and gradually the phosphorescence will fade away. And we're getting close to the end. So this is a cycle whereby the speed ramps up and then falls back down. Now we're fine-tuning the detection system. You have the control electronics that gives you the rotational speed. So a couple dozens of hertz, and you gradually increase it. And meanwhile, you look at the signal from the photodiode. Our starting point was 80 millivolt. And as you can see, the signal gradually increases until it gets to maybe 200, 220 millivolt at a maximum modulation frequency. The interpreter can barely hear the streamish noise. Now, Becquerel used rotational speeds to achieve 3,000, 4,000 hertz. But this device only gets to 1,000 hertz. We could do better, but again, this is off-the-shelf equipment. This gives you some idea of how good Becquerel's instruments were back in the day, that he's able to do better than we can now. Now, the modulation frequency. We are able to record the signal for each frequency. And this gives us a graphic curve that matches the growth in the outgoing signal from the phosphoroscope as speed increases. So we're able to build this into a model. We turn the graph into a model using this equation. There are two important parameters. First, the modulation frequency, and then tau, the characteristic time for the energy degrowth. And then we look at the value of tau. This is the blue curve that you see on the graph. So we have a very good result, and this gives us tau. So the relaxation time is about 0.3 millisecond. Obviously, that's something that Becquerel could not have done. He didn't have measuring instruments that were that accurate. But this would also involve a number of hypotheses that are based on quantum mechanics. And also, Becquerel wasn't a big believer in mathematics. He was a very effective and efficient experimenter, but he believed in applied physics, not theoretical physics. And the photophoroscope does not achieve the modulation. As like I said, this reenactment does not achieve the same results that Becquerel did back in the day. That's how good his instruments were. So a couple of modern applications. Now, this whole concept of rotating wheels or rotating mirrors, this was used until the 1960s in off-the-shelf spectrophotometers. Those were available in the 1960s. And then in terms of fluorescence, there were lots of consumer applications such as LEDs. And in detergents in particular, there are optical brighteners so as to make your sheet look whiter than white. So optical brightness convert part of the light from the invisible to the visible spectrum and to make your laundry look whiter and cleaner. So also in the area of research, fluorescence is an idea that's used in biology in particular for imaging purposes. Autofluorescence of certain molecules is used in biological systems. We can also use external probes. This is an image obtained by one of our colleagues in her lab. So green means second harmonic imaging, and red means different kinds of tissue, which are autofluorescent. And this is how we're able to study the tissues. And this is high quality imaging but the resolution depends on the nature of the tissues. And there are other techniques as well measuring the fluorescence time, a bit like what I said before. And this parameter will be used as a characteristic marker of tissues. But obviously, this is highly technical. I'm not going to go into that. Now, phosphorescence. I would say that there are fewer direct applications. I'm thinking, obviously, of quartz, Casio, glow-in-the-dark watches. Here's another example. Biological imaging probes use long lifetime phosphorescence sources. They use it for imaging purposes. Thierry Gacoin and other colleagues from the lab are developing these systems. And by way of conclusion, of course, I'd like to extend my warmest thanks to Polytechnique and to the class of 2018 who were involved in my project. Many thanks to Thierry Gacoin for providing the phosphorus. And also many thanks to the team, to the musics team at Polytechnique School. Many thanks for your attention. Thank you very much, Guilhem Gallot, for this excellent, fascinating presentation on Edmond Becquerel's phosphoroscope. It was so interesting to actually see it work. I have a quick question. The Queisser oil lamp, did it work? Well, it's an oil lamp. But it's a highly complex oil lamp. There's a regulation system. The oil flow rate can be regulated so as to ensure consistent brightness. To ensure perfect stability of the light source. I understand. So these lamps were used only by scientists. They were very expensive to make. And so these are works of art today. You can find a few of them available on the market, but they are very rare and valuable artifacts. We have a question from Mohammed Sharif. The two rotating discs are connected to each other, but do they turn relative to each other? I think it's going to be an easy answer. You're absolutely right. This is exactly it. Now, getting back to this picture, see the two wheels, the blue one and the green one. Yes, they turn at the same time. They are connected to each other. But there's never an alignment between the two apertures. No other questions. Once again, many thanks to Guilhem Gallot for his fascinating talk. Thank you for listening. Okay. Taking back the microphone, thank you. I'm now going to introduce the next speaker, François Guillemot. But before I introduce him, I would like to emphasize his many responsibilities. He's a deputy director at IPVF, but before that, he was also deputy director at Gaudet. And this is what I've written down. He was also the director of NextPV. NextPV was a joint laboratory effort with Japan, the Tokyo University in particular. And he had a lot of fun doing that. He had a lot of fun developing a number of concepts. Obviously, he's interested in materials, perovskites, and all other new emerging materials, but he had a lot of fun developing these concepts pertaining to the interaction between light and matter and different kinds of cells with hot carriers in particular. So this is a gentleman who's developed a number of techniques for optical spectroscopy to study materials for solar cells in particular, and other electronics components. In particular, he has an interest in the interface surface properties. And as you can well guess, things often happen at the interface. Without further ado, I'm now going to hand over to Jean-François. We're looking forward to hearing his presentation on phosphorescence and the ultimate yield or efficiency of solar cells. Handing over to my colleague.
Thank you very much, Jean-Louis. Thank you to the organizers for having invited me to talk about this fascinating topic on the occasion of the bicentennial anniversary of Becquerel's birth. So I'm going to speak in French. So what is the link between luminescence and photovoltaics? In fact, at the time of Edmond Becquerel, it was a non-trivial action of light on materials. Anything that doesn't produce heat. We talked earlier on about photovoltaic effects on detectors and actinometers, anything that produces electricity with light, or it could be phosphorus that produces energy. It could be photography that produces chemical changes based on light. And today, what remains today of this connection? This connection is extremely important to the point that it is, in fact, a standard in the industry. If we take silicon, and 95% of solar installations use silicon. So we have a lingot that is uh, made into bricks, then wafers, and then PV cells. At each stage in the process, we'll be able to look at this, and this is what is done generally. The luminescent the luminescence or the intensity of luminescence on cross sections of these bricks, wafers, and on PV cells will be able to correlate the intensity of luminescence with the performance. We can do this online with a quality control following an assembly line, and we can control more than one wafer per second in a production line. We can do even better. We can look at the luminescence of solar modules at the time when they are exposed to sunlight in the field. You can see in this image here, you see here the spectral intensity of the luminescence in this red line. So with the commercial silicon compared to the intensity reflected by sun in normal conditions. And you can see this intensity is of a few percent. With modulation techniques, elaborate modulation techniques, we'll be able to extract this luminescent signal, and we can, with modules that are exposed to light, we can have images that are similar to those that we can produce in a laboratory and in much better controlled conditions. So if we're able to do this, we can put these cameras on drones and inspect solar fields or solar farms, and to detect any failures or breakdowns. It's extremely useful and precise technology. So what I'm going to talk about in the rest of my presentation is the science behind this photovoltaic effect and the luminescence, and to look how far we can go and how we can understand this, and then how we can attain the ultimate yield of these through these processes. So luminescence, we had an excellent presentation by Gallot, that is the emission of light follows excitation of photoluminescence and electroluminescence, but there are other types of luminescence that also can be obtained. You have fluorescence, fast photoluminescence, fast process. Now, generally, uh, this the contribution of Becquerel was in this area. So if we look at resemblances between a luminophore and a solar cell. Now, a luminophore absorbs light. This light promotes electrons at the highest level of energy. The image of the flipper by Daniel Lancourt, this excitation will move around in the material, and eventually, after a certain amount of time, either the electron will reach a level where it emit a photon, or it will emit heat. In a solar cell, it's the same thing. The solar cell is a material that's going to absorb light, produce excitations, they're going to wander around, and eventually emit light. Now, to do one thing more, we're going to be able to recuperate current. These electrons can be recuperated via the electrodes and to put it in external circuit before bringing it back. So we're going to have two systems. We have two systems which are energy conversion systems, which are very similar. And since they're similar, they follow the same physical phenomena. And there's something very interesting. When you look at the physical phenomena that are similar, you can find exact relations that link them together. In 1959, it was discovered that what absorbs emits for each wavelength, that the fact that a material can absorb light can also emit light. So what absorbs should emit. There are all other reciprocities that have been were revealed during the 19th century. After 1859, there was electromagnetic reciprocity. There are also links between temperature and the light that can be emitted, Max Planck, black body radiation, and there are many other relations of reciprocity between flows or fluxes of particles and forces. Lars Onsager, for example, in 1931. Now, in photovoltaic, there are many lists of reciprocity that were studied. For example, Van's Rosbreck in 1954. And I'm going to talk about one which was identified by Araujo, the emission of photons, but also the injection of collection of photons. We have a reciprocity between the photoelectric effect and luminescent. So when you light up a photon, you can recuperate charge carriers. Conversely, a lead is a diode. When you inject charge carriers, you recuperate photons. And these are two phenomena resemble one another hugely. So what makes a good solar cell? Well, a good photo cell absorbs light and it generates an electron that's mobile. If it's mobile enough and its life is long enough, it'll be able to give rise to the generation of electric energy. So in terms of distance and energy levels, you have the photon, you'll be able to, they're going to go through the solar cell and promote electrons, and the energy emitted and the excitation is very fast. It's going to bring the electrons to if there's a sufficient slope, if these electrons lose energy, they can join the lower level. We'll have a third phenomenon. So there are three loss elements over a time scales that are relatively different. Unused photons, thermalization, and collection and recombination. These are phenomena which are linked, and we recuperate the energy. This model of solar cell has given rise to the Shockley Queisser model, which is a rather ideal model in which they simplified things. They considered the energy of photons were not absorbed, but when a photon was absorbed, it gave rise to either an electron, a mobile electron that could be collected. If it wasn't collected, it was given to another photon. So there's one photon for an electron and so on. So by simplifying somewhat, we come to a description which only depends on its optical properties, and we can have emission or a collection. This very simple model makes it possible to give a threshold or limit, a limit of yield. So you see here this curve in blue, that's the convertible power. It's roughly 30%. And most of the energy is either thermalized, if the absorption is too low. So if there's a very high energy, it's dissipated in heat. And if it isn't very high, most of it is absorbed. In the best solar cells, we're very close to this limit, to this threshold. So that means that since they're optical properties, we can understand that what determines the yield of these solar cells, we're going to be, through luminescence, we'll finally understand how these solar cells function. Here you have, if we look on the left, you have a spectrum energy, intensity of the photons, and you have a photoluminescence spectrum. And here it has several characteristics. What we see that first it has a maximum, a peak, and the intensity at the peak. And this is linked to the free energy per particle that is available for the photovoltaic conversion. And now this is associated to the distribution of the carriers, and that is their temperature. The peak itself, its position, depends on the absorption threshold of the material. And here, the part with the lower energy is associated with certain defects in the material. So we can have access to the absorption properties of combined absorption properties of the material. You have an element of volume that can be explained in this manner. And it is, in fact, a rewriting of Planck's law with the terms of absorption of emission. And here, two terms. The energy activation is reduced by the excitation of the material. So the energy, the free energy, is in fact the tension or the voltage, the work, and the temperature. And we see that, in fact, the luminescence, its intensity, gives a directly linked to thermodynamics. It's not just a theory, it's something that can be proven. When we look here, the contact and the collection grid, this cell is exposed uniformly to light. And what we measure, we have a spectrum. Camera makes it possible to measure the spectrum at each point. And you have here, you see it here at a logarithmic scale. Now, if we inverse this formula, we have the absorption rate. And we can have access to the temperature and this free energy, which can be divided by the elementary charge with a voltage. And we see that voltage that we extract from the solar cell is equal or very close to what can be measured electrically in the same conditions. So we have a relationship which it functions. We can extract the energy and the possibility of conversion for each solar flux, and we can see what the characteristics of the solar cell are without any contact. And we can see what we do with or without contact. We have access to the local yield for each point for good solar cells with a very low rate of margin of error. So that's spectral luminescence. This is very often, you can send a light punch on the solar cell and collect mobile electrons, be emitted different time frames. So we'll have a reduction over time, but it's going to produce the spectrum, different spectra depending of intensity, depending on time, which are linked to the kinetics of the transportation. We can also, with cameras, look at how the carriers migrate through time and emit light with a punctual excitation. and see how the light is diffused in space, and also gives us another way of having access to the migration of the electrons in the solar cell, which are necessary to be able to collect the electrons. So we have another instrument that is going to be a part of flash. So we're going to have, for each dot, we'll have the luminescence. And by observing this temporally, we're going to see the intensity of the luminescence for the different images. We can have images that over a temporal, over a time frame, we have different intensities in different times and extract parameters. With one experiment, we can extract all the parameters that are important: surface, length of diffusion, range of diffusion, and the life expectancy of the different bands. If we compare this with a spectral examination of luminescence, for example, spot checks, we can see the transport of photons or photon recycling. So photons can be used several times in the same cell. We can do many other things too. I'm going to be rather brief because there's a lot to talk about. We can also have access to the collection probability with the work of Martin Green, for instance, how to use luminescence, properties of luminescence. So the last point I would like to address is, can we go beyond? What I said is the Shockley Queisser model propose limits of conversion at 33%, and we're using all of the solar spectrum. I mean, this is because we have two mechanisms. We have a thermalizer mechanism for photons that are high energy, and non-attraction for photons that aren't sufficiently energized. And we know that the best systems that have been produced in laboratory reach 47%. And we're talking about multi-junction panels, and I'll explain this later. And the theoretical model says we'd have much high yields, up to 87%. To achieve this, we need to have radiative, high radiative efficiency, and we have a whole series of solar materials for the amount of photons emitted to be very good phosphorus. So the yield as a function of the yield obtained in cells, you have an excellent correlation. And the best cells, the ones that have the best radiative yield. So this is acquired for a great number of solar materials. It's envisageable to produce solar cells very high yield. And I'm going to present two approaches, one which is called multi-junction, and the other one is a hot carrier solar cell. It enables to achieve this high yield, but there are other ways which could be examined with luminescence techniques, with a multi-exciting generation, with up and down conversion, where we'll use photons that aren't sufficiently energized, that wouldn't be absorbed, convert them into photons that are absorbable. And with very energetic or energized photons, we'll be able to produce much more. So if we talk about multi-junction system, it's very simple. We'll have multicolor wideband radiation, which will be divided into, by a prism, into different spectral bands. The blue would be absorbed by a high threshold absorption, be able to have a rather high voltage, and the red photons will be absorbed by a cell with another band. So each spectral band can be absorbed by a cell which will be optimized for this. And we can pile these different cells. So the blues will absorb the blue spectrum and so forth. And we can even stick these different cells together and can have much cheaper solar cells. So here you have a picture that represents these cells that are piled on one another and interconnected. Some are going to absorb the blue, others the green, and others the red and infrared. These cells are integrated multi-junction cells. We can measure high yields, but we cannot have access to the yield of each cell. And since they're in the series, they are traversed by the same current. And if one of them is faulty, that's not going to be easy to identify. So what we can do is have these cells function and observe the luminescence of each of the cells that is part of the pileup of cells. And based on this luminescence of each of these individual cells, be able to, here you have the measurements, the intensity of photons to extract the voltage for each of the cells, and we'll be able to identify the total current, which can be, so we break it down, and to each spot of this solar cell, we can see how the system is functioning. And you have, for instance, here, for a multi-junction cell between two gray, you have a collection efficiency can be measured for the different layers of that cell. Now, to go to something a little bit more exotic, we can also depart from the hypothesis that the carriers which are photogenerated in cells are thermalized. When it's the case, indeed, for a single junction, the limit is around 33%. But we know with strong, high intensity of excitation, we can have a photo-generated carriers that are not thermalized, and we can have a much higher yield. So we're going to produce, as is the case here, as is illustrated, we'll have a spectrum which would resembles a GIS as a little bit luminescence. If we increase the intensity, we can see that the high energy section will be increased. And we have, we can measure the temperature of these thermalized carriers. We can set up devices where we can measure the current, and we can demonstrate experimentally the yield of this system. And what we realize, in fact, is that since we have thermalized carriers, the increased energy that is recovered is analog to a thermoelectric effect. These carriers, by cooling down, are going to increase the voltage delivered by the solar cell, and therefore increase the potential yield of these systems. So we can measure the effect activated by light. So this means there's the possibility to map different temperature gradients, and we can measure voltage gradients with this system and measure the Seebeck bipolar effect, as you see here in the illustration. This enabled us to measure the thermoelectric effect. So you have here summarized, great many measurements can be carried out thanks to luminescence. I haven't illustrated all of them because there are others. And we have correlation measurements, polarization measurements. It's a field that is extremely active. And to sum up, I tried to show you that luminescence gives a fingerprint of photovoltaic energy conversion process. It's linked to all the different reciprocity relationships that enable us to know how a photovoltaic absorber is capable of converting the energy that it receives into photovoltaic energy, electric energy, with a special resolution, and how this can be resolved spatially and temporally. So there's a lot of information. We can improve the yield, and tomorrow we'll have very high solar cells, would be the ultimate solar cells, with very high yields, and possibly even using a number of devices, systems in the future that will enable us, thanks to these relations of reciprocity, to go even further in this process. And now I would like to thank the laboratory, the photovoltaic laboratory at IPVF, and other laboratories with whom I have very interesting discussions, and I'm ready to take your questions now. Thank you, Jean-François. Yes, this was very exhaustive, and I really appreciated this. There's a question. We often say a good semiconductor is a semiconductor that emits light. So luminescence and absorption are indissociable. I think you've clearly demonstrated the problem of solar cells compared to a laser diode. The distribution of energy of the electrons is weak, and the spectral distribution is also very weak. So we come back to the problem that Edmond Becquerel posed with the spectrum. In a single cell, the spectral distribution is very wide, and unfortunately, we recuperate the electrons with a low energy distribution. So this would deserve hours to discuss and see how we could find a new concept to recuperate these thermalized carriers or hot carriers, and how to recycle the photons. And the question that we have is one by Mohammed Sherif, and the first thing that was not clearly understood. Now the yield in the explanation of the yield limit, is it due to the material? That was the first question. The second question is more specific. The photoluminescence is not of the cell itself, but of the material itself. Is it linked to the cell or to the material? That is the question. Now, it sort of refers to the silver nanoparticles and how this has an impact on absorption. These are excellent questions. Indeed, luminescence is that of the materials. But I'm trying to show to you that the material that absorbs is the material, through this material, it's the energy that goes into the solar cell, and it is that it's active. The rest are passive components in the cell. Anti-reflection layers that enable the light to penetrate within the cell, can be contact grids, or materials that make it possible to extract. They don't convert the energy, they transform it. So the core of the machine, the motor of the solar cell, is the absorber. That's where the conversion takes place. And it's this conversion process that we can look at with luminescence processes, which produce the image, the exact image, or a very precise image of what's going on. This is relationship between the material, and there are parasite absorptions in cells, and there are, of course, other absorption phenomena. And these phenomena, we're not going to see them directly via luminescence. They're going to impact the yield of the cell indirectly. But these phenomena would require other techniques. Now, another aspect I may have forgotten. Yes, the silver particles or nanoparticles. Now, that's very interesting, the silver nanoparticles, because it was a little bit difficult to talk about this in the presentation, but it is linked to work on photography, and it directly relates to what was presented by Francesco and Lucia earlier on the plasmons. And of course, the thesis that was done at the history of the Museum of Natural History. And we see that they interact with light and they concentrate the energy, solar energy, and are today a subject of research which is extremely vibrant and very active in solar cells. Just next to IPVF, we have a laboratory that's working on this, and this will be done to facilitate the collection of the photon, to improve the absorption of the photons, and these solar cells will be much thinner, so it can be able to use smaller quantities of material. We'll be able to use more exotic processes with thermalized carriers that could be greatly improved if we can use plasmons as they were demonstrated in previous presentations, which are also able to transfer the energy efficiently and put this system in a state which is excited further. And so this also relates to extreme light, what can be done with extreme light, which was discussed earlier on. Thank you very much. Well, we don't have, there's another question, but we don't have much time. The question was, Emmanuel Bois, can we check PV system with electroluminescence? Yes, what I showed you at the beginning, I don't know if we should go back to the other slides, but they will be put online so you'll be able to see them. But in the first slides that I put up, it's exactly what is done. We use electrophotoluminescence is used to control and to check installations, to detect. I don't think we have time to go back all the way, but it's something that can be used in industry and is used in industry today. In the field, in the solar farms, you could use electroluminescence and photoluminescence to check installations. So both are very much used.
Thank you. Time to conclude this session with Lawrence Peter, if he's available, and then move on to the rest of the symposium. Perfect. Thank you very much to Jean-Louis, Laurie, and Jean-François. As you may have noticed, we're behind schedule. How far behind? Half an hour behind schedule? Okay, so this is what we suggest. We can continue the discussion, have a more general discussion later today. Let's all go to lunch. Let's all go to lunch. For those of you who are on Paris time, so we apologize for being late, but we had such fascinating discussions. We hope you enjoyed them as much as I did. Handing over now to our two moderators, Alexandre. Alexandre will discuss the video session. It's important that you find the time by 2:30 to at least look at some of the video sessions. Thank you. So during the lunch break, feel free to check out our video testimonials. We have a number of guest video testimonials available to you. You can find the link in the Q&A box. They'll be available until 2:30, so only during the lunch break. Well, actually, we'll make them available to you once the event ends, so feel free to check them out. You'll find the list on the screen, and we shall reconvene at 2:30 p.m. Enjoy lunch!